All right, so for my next trick, I want to look at effective capacitance. So that basically means that if I have this set of capacitors here, what would an equivalent capacitor be? If I just wanted to use one capacitor, what would its capacitance have to look like? All right, and to do this, we've got some rules. I gave you the rules in the lecture. You add them if they're in parallel. You get more capacitance in parallel. That's like increasing the size of the capacitor plate, and you get less if you're in series. That's one after the other, and that's like increasing the separation between the two plates that we saw in 2 lectures ago. So how are we going to figure this out? Well, both of these guys, if you just did a line from one end to the other, both of these guys are in series with this guy. So actually, what we have to do is we have to collapse this part before we talk about that part. So we're going to have to do something. We're going to have to do the parallel part first, and then we're going to have to do the series part, and the series part will give us the answer that we want. So series, like I said, that makes things more, makes things longer. So that's going to be 1 over the effective capacitance is equal to 1 over the capacitance of one of these guys, which is 100 picofarads, plus 1 over the parallel capacitance. Okay, so first we have to do this part. We have to find the parallel capacitance. So the parallel capacitance is just, like I said, the sum of these two. So that's going to be C plus C, because these are both the same value. That's not particularly difficult because we have 100 puffs plus 100 puffs. Engineers tend to call picofarads puffs. I'm not completely sure why, other than it starts with a P and ends with an F. And so we add 100 and 100, and somehow we get 200 picofarads. So that's this part. We can collapse that into a 200 picofarad capacitor. All right, so like I said, this part is like a 200 picofarad capacitor, plus we're going to have a 100 picofarad capacitor. So these two diagrams are completely equivalent if we have a different size capacitor. These are all the same. This one's a little bit different, so these two are equivalent. So we can come over here and we can take the 100 picofarad first, that's a C, and then add in the 1 over the 200 picofarad, just like we saw in the lecture. Now this is equal to 2 over 200 picofarads plus 1 over 200 picofarads, which is 3 over 200 picofarads. Okay, so if we flip both of them over, that's 200 over 3 picofarads, which is equal to 66.7 picofarads. All right, and that's exactly what I had here, so I didn't screw that up too much. So again, how did we do this? Well, what we said is that if we have in our circuit two paths between 2 points that both go through different spots and then through another thing, then we have to evaluate that first. And actually, if we had really complicated circuits, we'd have to do the same thing, alternating between series and parallel, series and parallel. But we don't have that issue in this class really, because we don't want to make these things so hard. So the first part of this was to say, okay, well, I'm going to collapse these two paths, both of which can end up going, an electron or the voltage can go this way or it can go that way. Electrons don't actually go through there because they're capacitors and there's a break in them. So we collapse that and we have 200 picofarads and 100 picofarads for each one of these, and this is equivalent to that one. But then we can collapse this one more time into one capacitor, which is 66.7 picofarads. So first we had to use the parallel reasoning, which is just adding the capacitors. And then we had to use the series reasoning, which is doing this sum of the inverses. And the next problem is going to compare this with what we use for the resistors, which is going to be just slightly different. So I'm going to do the same configuration but with 100 ohm resistors in just a second. All right, bye now.